Hello everyone and welcome back. My name is Mr. Cobalt and in this video I'm going to go over Le Chatelier's principle and we're going to predict the effect of disruptions on equilibrium. So let's get into this. So according to Le Chatelier's principle, a system that is disrupted is going to react in such a way that's going to undo the disruption or undo the stress that was added to the system. So basically whatever you do to the system, according to Le Chatelier's principle, the system is going to undo it to get back to equilibrium. So, for example, if you add some product, then you've increased the amount of product that is now disrupting the equilibrium of the system. And so the system is now going to do what it can to do the opposite. It's going to get rid of the stress. It's going to do the opposite. You added some reactant, so it's going to get rid of that reactant. So it's going to use up more reactant. If you add more product, then it's going to react to undo that. So it's going to get rid of product, right? If you take away product, then it's going to undo that by adding product, right? So whatever you do, the system is going to do the opposite to undo that change, to undo that stress, to undo that disruption, right? So that's Le Chatelier's principle. And so we can explain these changes, we can explain these effects on the disruptions of the equilibrium by appealing to Le Chatelier's principle, but we could also appeal to what's going on with the reverse and the forward reactions. How are the forward and reverse reactions affected by this change that would lead to this moving of the equilibrium, either favoring left or right, or products or reactants. So let's get into this. So here we have our first reaction that we're given. Now I want to point out that we have kilojoules here on the product side. So what this is referring to is heat or energy that's given off as a product, right? So here we want to think of this as heat or energy in the form of heat, right? So here, this would be an exothermic reaction because heat is being given off as a product. Energy is given off as a product. So the great thing about this is that we can predict what the effect of temperature changes is going to be based on where heat is uh, in the reaction. Is it a product or a reactant? So here it's a product. So it's being produced during the reaction. So therefore, this is an exothermic. Exothermic reactions produced heat. If it was on the reactant side, then it would be an endothermic reaction. That means that energy would be absorbed by the reaction as a reactant and then moving forward. So how is temperature going to affect that? So we'll get to that in a moment. So let's start with A. So here we have an increase in N2 concentration. Nitrogen concentration is increased by adding more N2. So according to Le Chatelier's principle, if we're increasing the concentration of N2, then the reaction is going to shift in a way that's going to decrease N2 or remove N2. So since N2 is a reactant, it wants to get rid of N2, so it's going to shift in this direction to use up more N2 and get back to equilibrium by shifting towards the products. So from a perspective of the reaction rates, the forward and reverse reactions, we can understand this by the fact that if we increase the N2 by throwing that in there, that's going to speed up the forward reaction momentarily compared to the reverse reaction. So because the forward reaction now becomes faster than the reverse reaction, more product is going to be formed, more reactant is going to be used up, and so that causes the shift towards products. For NH3, for B, we're decreasing the concentration of NH3. So NH3, again, if you, whatever you do, whatever stress you put on the system, whatever disruption, the system, according to Le Chatelier's principle, is going to undo that. It's going to do the opposite. So here we are decreasing the amount of NH3, the concentration of NH3. So therefore, the system is going to increase that amount. And so therefore, it's going to shift towards the product. Since NH3 is a product, it's going to shift towards this way to make more product, NH3. So it's going to increase the NH3 concentration. Again, we can understand this by the reverse, comparing the reverse rate of the reaction rate and the forward reaction rate. So by removing reactant, right? So if we're removing, product. So since we're removing this, we're decreasing the amount of product here. And so that's going to cause the reaction rate, the forward reaction rate, to go faster because it's got to replenish that amount. And so it's going to go faster this way, and then compared to the reverse reaction momentarily. So that's going to cause an increase in the amount of product as the forward reaction increases, goes faster than the reverse reaction. Finally, okay, we have C for temperature increases. So this is where understanding endothermic, exothermic reactions is going to be important, and understanding heat is either as a reactant or a product. So if you understand heat as merely as a reactant or a product, just like NH3 is a product and H2 is a reactant, if you think of energy or heat being a product or reactant, then this will help understand how Le Chatelier's principle applies to here. So temperature increases. Well, what do you do when you increase temperature? How do you increase temperature? You add heat, right? So if you want to increase the temperature of water, you put the water on a stove, you turn on the heat, and it will absorb the heat and increase the temperature. So increasing the temperature means that you are adding heat. So if we think of heat as a product here, because it's an exothermic reaction, then we would be increasing the product. We're increasing the product of heat. So according to Le Chatelier's principle, if you increase products, then it's going to shift away from the products to get rid of. It's going to use up those products to create more reactants. So since heat is a product of this reaction, and we're increasing temperature, which means that we're increasing the heat, then that means we are adding heat, and Le Chatelier's principle is going to remove that heat. And so it's going to shift towards the reactant in order to use up the heat to get back to equilibrium this way. So that's how you can understand this from Le Chatelier's principle. From the forward and reverse reactions, we can understand it in this sense. So when you raise the temperature of the solution of the reaction, you're affecting both the forward and the reverse reaction. However, since this is an exothermic reaction, you're going to affect the reverse reaction more than the forward reaction. So therefore, the reverse reaction will be going quicker this way than going forward. And so that will cause more reactants to be formed, and therefore the equilibrium constant is going to shift towards reactants. Okay, what about D? Iron catalyst is added. So you add an iron catalyst to the reaction mix. How is that going to affect? Well, this Le Chatelier's principle does not apply to catalysts. So it's not going to have any effect according to Le Chatelier's principle. And then from the point of view of the reverse forward reactions, what catalysts do is that they affect the speed of both reactions, right? So what a catalyst do, it's not going to shift the equilibrium one way or the other. It just allows the reaction to approach and reach equilibrium faster. So it's not going to change the equilibrium. It's just going to allow it to come faster to equilibrium. So it's going to cause the reverse reaction to speed up at the same time that it causes the forward reaction to speed up. So both reactions, forward and reaction, speed up at the same time, and so you reach equilibrium quicker. So that's how catalysts work. So no effect on the equilibrium constant at all. Okay, so what about number two? Here we have this reaction. We have 3NO2 gas reacting with water gas, and then it's going to form HNO3 NO gas, and it produces heat again. So here we have heat. So we have heat being produced or energy. And so here again, we have an exothermic reaction. So it's producing heat. Heat is a product. So we can use that to help us understand how temperature is going to affect this equation. So here again, for A, we're increasing the concentration of water. So therefore, we're increasing reactant, since water here is a reactant. So if we're increasing reactant, according to Le Chatelier's principle, we want to decrease. So the system is going to decrease reactant. How is it going to decrease reactant? It's going to shift towards product. So more reactant is used up and more product is formed. So it shifts towards the product. Again, for understanding this from the perspective of the forward and reverse reaction, if we increase the concentration of H2O, then by increasing the concentration of H2O, which is a reactant, we're going to increase the forward reaction more and then the reverse reaction. So at that moment, the reverse reaction will be faster relative to the reverse reaction. So overall, more product is going to be formed compared to reactant being formed, even though they're happening at the same time. So that causes the shift towards making more product. For B, we have NO2 concentration going down. So here we have NO2. Again, that's a reactant, and we're decreasing the reactant. So by decreasing the reactant, that's going to cause the forward reaction to go slower, right? So if we decrease the reaction, well, let me explain from Le Chatelier's principle first. So according to Le Chatelier's principle, the system is going to do the opposite of what you do to the system. It's going to undo your change that you put in. So if we decrease the amount of NO2, if we decrease the concentration, then according to Le Chatelier's principle, the system is going to increase that concentration. So it's going to shift in this direction in order to increase the amount of NO2 that was lost and regain that equilibrium. So we're going to lose product and we're going to gain reactant. So it's going to shift this way. So from the perspective of the reverse and forward reactions, since we're decreasing, removing NO2 gas, so that's going to slow down the forward reaction. So then the forward reaction is going to go slower than the reverse reaction. And so at that moment, the reverse reaction is going this way more quickly. So it's going to form more reactant than product is being formed. And so therefore, we see that shift in the making of more reactant. So NO2 goes up. Next, we have a decrease in HNO3. So here we have HNO3 as a product. So we're decreasing product. According to Le Chatelier's principle, if you decrease product, the system is going to do the opposite. It's going to replace that product. It's going to increase that product to try to get back to that equilibrium or reestablish equilibrium. So we would expect it to shift towards product. So decreasing product is going to cause the system to shift towards product to make more product. So from the reverse and forward reaction perspective, since we're decreasing the amount of product here, that means we're going to be decreasing the rate in the reverse reaction. So when we decrease the rate of the reverse reaction, then the rate of the forward reaction is going to be faster at this time. So it's going to cause an increase in the making of the product here and compared to the making of the reactant. So more product is going to start to be made compared to a reactant being made. And so we see that shift in this direction towards product. D, we have temperatures decreased. So here we have a decrease in temperature. So again, we're going to go back and remind ourselves that heat energy here, the heat or energy is on the product side. So that means that we're going to treat this like a product like we did with NO and HNO3. So we're going to treat this the same. So if heat or energy is a product of the reaction because it's an exothermic reaction, and what are we doing when we decrease temperature? When we decrease temperature, we're taking heat away. We're removing heat. We're removing energy. And so in that case, we're removing a product. So from Le Chatelier's principle, so we're removing this product, we're taking it away, we're decreasing it. That means that Le Chatelier's principle says that the reaction wants to reproduce or reestablish or create more of that energy, replace the energy that was lost. So it's going to shift towards product, and therefore we would expect more products to be made shifting towards the products. From the perspective of the rates of the forward and reverse reaction, again, when you decrease the temperature, both the forward and the reverse reactions are affected at the same time. But because this is an exothermic reaction, the the forward reaction is affected more than the reverse, and so this is going to cause the forward reaction to move forward compared to the reverse reaction. So the reverse reaction is not going to be as affected as the forward reaction in this case. So finally, we have E. We're adding the RH platinum. So if you look at your arrow here, anytime you have information or either below or above the arrow, that's indicating the conditions under which the reaction is taking place. If you see something like this, like where you have platinum or RH, that's going to indicate a catalyst. If you have this is temperature, so this is telling you that this is happening under high temperature, 5 to 8 atmospheres. It's under high pressure. So these are the conditions under which the reaction is happening. And here we're being told in E that we're adding catalysts. So we're adding more catalysts to the reaction. Well, what is that going to do with the reaction? Well, for Le Chatelier's principle, the catalyst doesn't really have an effect on Le Chatelier's principle because the catalyst is not part of the reactants or products. So adding this is not going to have any effect on the equilibrium according to Le Chatelier. So it doesn't apply Le Chatelier. Le Chatelier's principle doesn't apply. But as far as the forward and reverse reactions go, adding more catalyst isn't going to affect the equilibrium because it causes the reverse and the forward reactions to happen more quickly at the same time. So it's going to cause the reverse reaction and forward reactions to speed up, but they speed up at the same amount at the same time. So all catalysts do is that they cause the reaction to reach equilibrium more quickly. It doesn't change where the equilibrium is. It's not going to cause equilibrium to shift left or right or towards products or towards reactants. So that's it for this video. I hope you enjoyed this video. I hope you learned a lot from this video. I hope this cleared things up for you. If it did, if you enjoyed this video, then please like the video, share the video with your friends, hit that like button over there somewhere. Maybe it's over here. I don't know. They move it. So just find the like button and just click it, okay? And then finally, also subscribe to my channel, please. And when you do, make sure you click the notification bell and then click all so you can be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you want me to go over, or if you have a topic you want me to cover, I would love to do that for you. Thanks for joining me and have a great day.